today we'll be going over the Maclaurin series of sine of x and cosine of x. Again, the Maclaurin series is just basically centered at x is equal to 0, whereas the Taylor series is centered at anything but 0. Okay? Now the Maclaurin series of f of x equals equal to sine of x, and then we'll do cosine of x later. It's just basically the sum of from 1 to infinity of 1 to the n minus 1 times 2n minus 1 over 2n minus 1 factorial. Alright? Now, the first 4 terms, if you keep plugging in 1, are, and sine is equal to this, the approximation, the first 4 terms of this would be x over x to the third over 3 factorial plus x to the 5th power over 5 factorial minus x to the 7th power over 7 factorial. Alright? So basically, as you can see here, Maclaurin series and Taylor series are just basically polynomial approximations. Now what that means is that they are just basically a sum of polynomials that approximate I guess more complex functions such as sine of x and cosine of x. Alright, now why exactly do we need approximations for them when, that might be your question. Well, that's because, let's say for example, instead of taking, sine, some x values you're used to, pi over 3, pi over 6, let's say for example if you took the sine of 1.7 radians. Now, as you can see here, it would be really hard to actually compute this because we're not actually used to taking the sine of these types of decimals. So, in this case, in order to actually do that, a good way of going about that would be using Maclaurin series or Taylor series, because these things are just sums of polynomial terms. And of course, plugging into polynomial terms are way easier than actually doing computations of sine of 1.7 radians. Now, of course, you could use calculators, but we don't always get that privilege on tests. So that's one way, Maclaurin series could be important, and along with including and Taylor series could also be important too. Okay, so and all this right here is just based off the formula for Maclaurin series, which is f to the n of 0 times x to the n over n factorial. Alright, it's based off that formula. And f to the n here just means, what derivative you're on so far. Okay, and when you kind of sort of use this formula here, you get the first 4 terms here, which then reveal the pattern equal to this. So that's basically how you do it. Basically, you'd use f of x, take its derivative as many times as you want, and then get these 4 terms here, or how many ever terms you need in order to get this sort of general term right here. And that's kind of the process of how most things go for Maclaurin and Taylor series. That's how you'd sort of derive this general term right here. So for f of x is equal to cosine, our formula would be n is equal to 0 from 2 to infinity. Okay, and then it would be -1 to the n power times x to the 2n, and then 2n factorial. Alright? And then our first 4 terms would be 1 minus x to the 2nd power over 2 factorial plus x to the 4th power over 4 factorial minus x to the 6th power over 6 factorial. Right? And that would be the pattern here, right? This right here, or this is actually the general term, or like the pattern. Okay. and this would be equal to cosine of x. Alright, so as you can see here, we have sine of x. We plug in x here. As you can see, it's accurate for the most part, but then after 0.5, it goes off towards infinity. So if you plug in our second polynomial term, we see that over 3 factorial, or just 6, we see that it's a lot more accurate than just using one polynomial term, or a first polynomial term. Okay? As you see here, it's accurate further than 0.5 and then goes off towards negative infinity. Alright, and then if you plug in or if we add our next term, which is just x to the 5th, right, we see that our function is a lot more accurate, and until about 2, and then goes off to infinity. So yeah, it's a lot more accurate than just 2 terms. So hopefully this is showing you that the more terms you add, the more accurate your polynomial function will be. Alright, we have our cosine function here, and if we put in our first value in, our first term of the series, we see that it's not very accurate in representing the cosine function. So we have to add in more terms. And when we do that, we see that 1 minus x to the second power over 2 factorial, or just 2, is a lot more accurate, because as you can see here, it's accurate from negative 1 to 1 here, okay? But let's just say we want to make this even more accurate. Well, you have to add more terms in, right? And when we do that, we see that 1 minus x to the second power over 2 plus x to the 4th power over 4 factorial, which is 24, is actually pretty good. It's pretty good approximation from negative 1.5 to 1.5. So again, the more terms you add, the more accurate your approximation function will be in replicating the cosine graph. Alright, that'll be it for the video. Thank you.